So we are into the important part of this unit. It is Radon Nikodym theorem. Important in the sense of conceptual wise as well as the marks it carries. And the weightage for Radon Nikodym theorem is 14 marks. So looking into the statement, let X be mu be a sigma finite measure space. So X be mu is a sigma finite measure space, and we have discussed what do you mean by a sigma finite measure space right at the start of this unit. And let gamma be a measure defined on B, which is absolutely continuous with respect to mu. So gamma is a measure defined on B, it is absolutely continuous with respect to mu. Then there is a non-negative measurable function, say f, such that for each set E in B, we have gamma of E to be defined as integral of f over E with respect to mu. So if we have that, then the function is also unique in the sense that if G is another function, any measurable function with that property, with carrying that property, then G equal to f almost everywhere with respect to mu. So the representation of this kind is unique. That what this line says, and I will come again the statement. Let X be mu be a sigma finite measure space, and let gamma be a measure defined on B, which is absolutely continuous with respect to mu. Then there is a non-negative measurable function, say f, such that for each set E in B, we have gamma of E to be equal to integral of f over E with respect to mu. Then this is unique, that is the function f is unique in the sense if G is any other function satisfying this property, then that function G is equal to f almost everywhere with respect to mu. So let me see on to the proof now. So to prove Radon Nikodym theorem, we need the help of these two lemmas. So we will get into these two lemmas for the first, and then we will move on to the proof of the theorem. So we have these two lemmas, lemma 1 and lemma 2, and we will not be seeing or having the proof of lemma 2, we will be proving lemma 1, and the proof of lemma 2 follows from the proof of lemma 1. So looking into the first lemma, let X be a measurable space. Suppose that to each alpha in a dense set, say D, of real numbers, there is assigned a set, say B alpha, which is in the collection B, such that B alpha is contained in B beta for alpha less than beta. Then there is a unique measurable extended real valued function on X such that f is less than or equal to alpha on B alpha and f is greater than or equal to alpha on X minus B alpha. So this is what we have as a lemma. Let me come again. Xb is a measurable space. Suppose that to each alpha in a dense set or D of real numbers, there is assigned a set B alpha in the collection such that B alpha is contained in, say, B beta for alpha less than beta. Then there is a unique measurable extended real valued function, say f, on the set X such that f is less than or equal to f on B alpha and it is greater than or equal to alpha on X minus B alpha. So this is what we have as a lemma 1. Before going into the proof of lemma 1, let me have a look also on lemma 2 and note the slight change in lemma 2 compared to lemma 1. So lemma 2, suppose that for each alpha in a dense set of real numbers, there is assigned a set B alpha which is in the collection such that mu of B alpha minus B beta is 0 for alpha less than beta. Then there is a measurable function such that f is less than or equal to alpha almost everywhere on B alpha and f is greater than or equal to alpha almost everywhere on X minus B alpha. Again, in both the cases, we have f to be unique. In the case if G is any other function satisfying these properties, then f equal to G almost everywhere. Again, let me come back to lemma 2 once again. Suppose for each alpha in a dense set of real numbers, there is assigned a set B alpha in beta in the collection B such that mu of B alpha minus B beta is equal to 0. So this is what the slight change we have compared to lemma 1. For alpha less than beta, mu of B alpha minus B beta is 0. Then there is a measurable function as that of in lemma 1 such that f is less than or equal to alpha almost everywhere on b alpha, and f is greater than or equal to alpha almost everywhere on the complement, so it's x minus b alpha. So this is what we have, and if you are not able to get it, please pause the video and have a look at lemma 2, because I am not going to repeat the lemma 2 again before proving the theorem. So before proof of the theorem, again I will not be repeating lemma 2. So if you want to have a look, please pause the video and have a look. So this is what we have, lemma 1 and lemma 2. So we will now move on to the proof of lemma 1. Now to prove the lemma, I'll be having for each x in the set x, for each x in x, I'll be having a function f of x, so that I am constructing it to be the infimum of the set, that is a set of all alpha coming from the dense set of real numbers, say D, such that f of x, where x will be in the set B alpha. So I am having a set now for each x in x. I am constructing a function f of x to be the infimum of the set of all alpha coming from the dense set of real numbers D, such that x will be coming from the set B alpha. So now having this, I will be constructing a function, or I will be showing that this function satisfies all this property what we have learned in this lemma. So clearly, if this is an empty set, and as usual we have infimum of empty set to be infinity, so that we will be having, if x will be in B alpha, then that implies f of x must be less than or equal to alpha. So clearly, if x will be in B alpha, I will be having f of x less than or equal to alpha. If not, if x will not be in B alpha, then x will not be in this, say some B beta, such that for every beta less than or equal to alpha, less than alpha, strictly less than alpha. So if the x is not in B alpha, then x will not be in B beta for every beta less than alpha, so that given implies then f of x will be greater than or equal to alpha. So having constructed the function f to be such an infimum of such a set, we are having x to be in B alpha, f of x will be less than or equal to alpha, and if x is not in B alpha, that is the complement of the set, then f of x will be greater than or equal to alpha. So now having constructed f of x to be as like this, we are having all the criteria that should be satisfying for this lemma, except that we are remaining to show that there is a unique measurable extended real valued function, so that we are remaining to prove that f is measurable. So now our claim is to be f is measurable. If you again come back to the lemma, xb is a measurable space, then each alpha in a dense set of real numbers, we have that is assigned to a set B alpha in beta in B, such that B alpha is contained in B beta for alpha less than beta. Then f satisfies f less than or equal to alpha. If it is in B alpha, then if it is not in B alpha, it will be greater than or equal to alpha. Just we are remaining to prove that f is a measurable function. For this to prove, I will consider for lambda to be in R, so lambda is in R, I will consider or try to construct a sequence, say alpha n, in the dense set of real numbers D, such that alpha n is less than lambda, and also the sequence converges to lambda. So for choosing lambda to be in R, I am trying to construct a sequence, say alpha n, in the dense set of real numbers, such that alpha n is less than lambda and the sequence is converging to lambda. I can justify this, that the choose of such a sequence in the dense set, say D, by an example, and we know that the set of rationals is dense in R. So Q is dense in R, so that I can choose a sequence like say alpha n that is converging to lambda, because if I choose xn to be in Q and xn to be in lambda 1 minus 1 by n, lambda plus 1 by n, so as Q is dense in R, I can choose such a sequence converging to lambda, because if I choose xn in Q and xn to be in lambda minus 1 by n, lambda plus 1 by n, then that implies mod of xn minus lambda is less than 1 by n. So clearly the absolute difference between xn and lambda is less than 1 by n, and xn converges to lambda as n tends to infinity. So this is the example which justifies to choose such a sequence in the dense set of real numbers, so that the sequence converges to lambda, where lambda is in R. So now we will move on to show that f is measurable. So now to prove that f is measurable, it is enough to prove that the set of all x, that f of x is less than, say, a real lambda is measurable. So to prove f is measurable, we will prove that this set, which is set of all x, that f of x is less than lambda, for lambda to be real. If this is measurable, then that implies f is measurable. But to prove this set to be measurable, we will show that this set is same as union of b alphas. Union of b alphas, say b alpha n, where n running from 1 to infinity. And again, one can have the question, how can one say that showing that this set to be union as b alpha n's, then that implies this set is measurable? Because choosing b alphas to be from the collection B, and the collection B being a sigma algebra, b alphas are measurable, so that union of b alpha n's, which is a countable union of measurable sets, is measurable. So as that union is measurable, this set will be measurable. So if this is measurable, then that implies f to be measurable. So to prove that f is measurable, it is enough to prove that this set is same as union of b alpha n's, so that the union being a countable union of measurable sets, which is measurable, so this set will be measurable, and that implies f is measurable. So to prove the continuity in this the sets, for the first we have, if f of x is less than lambda, then clearly we have f of x to be less than that of the sequence, which is less than lambda. Then clearly by the definition, that implies x will be in b alpha n's, so which implies x is in union of b alpha n's. So taking x to be in the such a set, we have x is in the union, so that implies this set is contained in the union of b alphas. So again, on the other side, if I take x to be in union of b alphas, then that implies x is in b alpha n for some n. So having x to be in b alpha n for some n, again I have this by the definition, f of x to be less than or equal to the sequence, which is less than lambda, and that implies f of x is less than lambda. So that implies x is in the set of all x such that f of x is less than lambda. Again, choosing x to be in the union of b alphas, I have x to be in that set. So that implies union of b alphas is contained in the set of all f of x less than lambda. So these two implies the equality of these two sets. So that implies this set is measurable. So that implies f is measurable for each lambda to be in R. So this concludes the proof of the lemma. But f is unique. So such a f in the lemma is unique. So to prove the uniqueness, it is left to you, which will complete the proof, and we will move on to the proof of the theorem. So coming into the proof of the theorem, and again recall the statement of the theorem right from the start. And at the start we have the space x b mu to be a sigma finite measure space. So at the start of the statement, we have x b mu to be a sigma finite measure space. Again, recall the statement of the theorem. So having x b mu to be sigma finite measure space, it is not at all so difficult to extend the case of finiteness to that of sigma finiteness. So as it is not difficult to extend that of finite case to sigma finite case. I will still assume mu to be finite. So I will assume still mu to be a finite measure so that if I consider D to be Q and having known that Q is dense in R, then alpha will be in Q. So having this, I will consider the mappings of the measures gamma to be from B to 0, infinity union infinity, and measure mu to be B from 0, infinity. So having considering the maps of gamma and mu to be so, we clearly have gamma minus alpha times mu to be a signed measure. So having gamma and mu to be such a maps, we have clearly gamma minus alpha times mu to be a signed measure for each alpha in rationals. So alpha is in rationals now. So for each rational alpha, I have this to be a signed measure. Again, with the help of Hahn decomposition theorem, as this is a signed measure, we can have the decomposition of this measure. So let decomposition of the set, say A alpha union B alpha be equal to X, along with that A alpha intersection B alpha is empty. So this is a disjoint union of A alpha and B alpha, so that it is equal to X. Now this is the Hahn decomposition, and I will set A naught to be the whole set X, while B naught to be equal to empty. So at the start I will have the decomposition to be A naught equal to X and B naught to be empty, and then if I consider B alpha minus B beta, that is same as B alpha intersection with B beta complement. So B alpha minus B beta is now equal to B alpha intersection B beta complement, and I will call B beta complement to be, say, let it be A beta. So complement of B, so it will be A beta. Now I have B alpha intersection A beta, where B alpha is a negative set with respect to the sign measure gamma minus alpha mu, and A beta is a positive set with respect to the sign measure. So having this and this to be negative and positive sets, if I consider the product gamma minus alpha times mu with B alpha minus B beta, since B alpha is negative set, then gamma minus alpha mu will be less than or equal to 0. The product is less than or equal to 0. In the same fashion, we have the gamma minus beta times mu into the same B alpha minus B beta to be greater than or equal to 0, since A beta is positive set. So gamma minus beta times mu, the product will be greater than or equal to 0. And for my convenience, I will call this to be inequality 1 and inequality 2. Now on multiplying minus to inequality 2, I will be having minus of gamma times gamma minus beta times u into B alpha minus B beta to be less than or equal to 0. As I am multiplying minus, the inequality sign changes, and I will call this as 3. Now adding inequality 1 and 3, I will be having adding inequalities 1 and 3, so that B beta times mu into or B alpha minus B beta minus alpha mu into B alpha minus B beta, as both are less than or equal to 0, that will be less than or equal to 0. So beta times mu into B alpha minus B beta minus alpha times mu into the same thing is less than or equal to 0. And taking the things in common, beta mu minus alpha mu into B alpha minus B beta is less than or equal to 0. Still, if I take mu as common, beta minus alpha times mu into B alpha minus B beta is less than or equal to 0. Again, observe the case that here we have beta to be greater than alpha. So as beta is greater than alpha, we have this to be positive. So since this is positive and the product is less than or equal to 0, we must have this to be less than or equal to 0. So we have here mu of b alpha minus b beta to be less than or equal to 0. But we know that mu is a measure. So having defined mu to be a measure, we always have mu times b alpha minus b beta greater than or equal to 0. So by these two inequalities, we have mu times b alpha minus b beta to be equal to 0. Now having mu times b alpha minus b beta to be equal to 0, again recall the lemma 2. If mu times b alpha minus b beta equal to 0 along with beta greater than alpha, then we can find a measurable function, say f, satisfying f to be less than or equal to alpha on b alpha and f to be greater than or equal to alpha on x minus b alpha. So we can find a function f so that given that mu times b alpha minus b beta equal to 0, whenever beta is greater than or equal to alpha by lemma 2, so we are now able to find a function f such that f is less than or equal to alpha on b alpha and f is greater than or equal to alpha on x minus b alpha. Now if we have alpha to be equal to 0, then we have gamma minus alpha times mu is same as gamma. So alpha is 0, we have this, and also x was a alpha union b alpha with a alpha intersection b alpha to be empty, and if we set a naught to be x and b naught to be empty, then this was the case. If this is the criteria, we can choose f to be non-negative. So we can choose f to be non-negative because if I choose if f, then f is less than or equal to 0 almost everywhere on the set b naught, which is equal to empty set, and f is greater than or equal to 0 again almost everywhere on the set a naught, which is whole of x. So these two things suggest us that f is clearly a non-negative measurable function. So we are choosing f to be non-negative measurable function on the criteria that f is less than or equal to 0 almost everywhere on b naught, and that is an empty set. So we have b naught to be empty and f greater than or equal to 0 almost everywhere on a naught, which is the whole of x. So this was the kind, we have the decomposition of x into a alphas and b alphas, and that was a disjoint union, so that if alpha is 0, we have that to be equal to gamma. Now having chosen this to be f to be a non-negative function, then I will define if E is any arbitrary set in the collection, say B, we have the collection B, and if I choose E to be any arbitrary set in B, I will define a set, say EK to be intersection of E with BK plus 1 by n minus BK by n. So choosing E to be any arbitrary set in the collection, I am defining a set EK to be such a set that is intersection of E with BK plus 1 by n minus BK by n. And also E infinity is same as E minus union of BK by n, and union is running from 0 to infinity, k from 0 to infinity. So E infinity will be E minus union of Bk by n, so that we will have our set E to be same as E infinity union of Ek's, again k from 0 to infinity. So having chosen arbitrary E in the collection, I have Ek to be of this kind, and also E infinity is E minus union of Bk by n, and so that E will be our set E infinity union of Ek's. So I have E to be such a set now. So having E to be such a set, so if I choose x in Ek, then choosing x to be in ek, clearly if x is in ek, then x will be in bk plus 1 by n. So that implies x will be in bk plus 1 by n. So having chosen E to be such a set, if I choose x in ek, I am having x to be in bk plus 1 by n. So that suggests us that k by n is less than or equal to f of x, and that is less than or equal to k plus 1 by n almost everywhere on the set ek. So if x will be in bk plus 1 by n, then I can find a bound for the function, say f, which is our non-negative function we have chosen, so that k by n and k plus 1 by n are bounds, and this is almost everywhere on the set ek. Now integrating all on the other sides with respect to mu over the set ek, we have integral of f over ek with respect to mu, and integral of k plus 1 by n over ek with respect to mu. Integrating all this, I get k by n, and this is by definition of a Lebesgue integral, this is mu times ek, and if I choose this to be, say, gamma of ek, we will come to know that, and still this will be less than or equal to k plus 1 by n times mu of ek. So again, clearly these are bounds for gamma of ek, and if I consider 0 less than or equal to the absolute value of integral of f over ek minus gamma of ek, this will be less than or equal to k plus 1 by n gets cancelled, and 1 by n times mu of ek. So I have 0 less than or equal to the absolute difference of integral of f df minus gamma of ek to be less than or equal to 1 by n times mu of ek. And clearly this tends to 0 as n tends to infinity. As n tends to infinity, clearly this tends to 0, so that we have f d mu integral of f over ek to be same as gamma of ek. So that problem was already reduced here as we choose the decomposition of x into a alpha and b alpha, so that f is a non-negative measurable functions. Our problem was already reduced to show that the integral of f is same as gamma of ek. So having chosen the sets ek and e to be of this form, we got the bounds for f, and integrating we arrived at the thing that integral of f is same as gamma of ek, so that this suggests us that gamma is absolutely continuous with respect to the measure mu. So we have gamma of e to be 0 for each set e for which mu of e is also 0. So we got gamma of e to be 0 for each set e for which mu of e is also 0, so that it implies gamma is absolutely continuous with respect to mu, by which we got integral of f over ek to be gamma of ek. So next we have f to be equal to infinity on e infinity. So having f to be equal to infinity on e infinity, we have two cases here. One is mu of e infinity to be 0, and the other mu of e infinity to be greater than 0. For the first case, if mu of e infinity is 0, then clearly integral of f over e infinity is 0, as because gamma is absolutely continuous with respect to mu, and if mu of e infinity is 0, that implies gamma of e infinity equal to 0, so that clearly integral of f is 0 and gamma of e infinity is 0. So we have integral of f over e infinity to be same as gamma of e infinity in the first case where mu of e infinity is 0. Next, what if in the second case mu of e infinity is greater than 0, having f to be infinity on e infinity? Again, see that e infinity was a set that defined as e minus union of bk by n's, and union was running over k0 to infinity. So E infinity was our set defined as E minus union of pk by n's. So if I take x to be in E infinity, then x will not be in the union. So x will be in its complement. So say x will be in the some intersection of ak by n for k greater than or equal to 0. So for every k greater than 0, we have, if x is in E infinity, since our E infinity was the set defined as this, clearly if x is in E infinity, x will be not be in this union, so it will be in this complement, say intersections of ak by n. So having this, since x is in intersections of ak by n, x will be in ak by n for every k. So having x to be is in intersection, we have x to be in ak by n for every k, so that f is greater than or equal to k by n for k greater than 0. So we have f to be greater than or equal to k by n every time for k greater than 0, so that we have f to be equal to infinity in the case mu infinity is greater than 0. Similarly, if I choose as E infinity is contained in ak by n, E infinity is contained in ak by n, I have, if I consider gamma minus alpha times mu, and if I take alpha to be k by n, so k by n times of measure of E infinity, this is greater than or equal to 0, or k can be greater than or equal to 0, so k greater than 0. I can take this to be gamma of E infinity to be greater than k by n times of mu infinity, again for every k greater than or equal to 0. Since this is for every k greater than or equal to 0, we have mu of E infinity, gamma of E infinity to be greater. So clearly we have gamma of E infinity also to be equal to infinity. So we have f to be equal to infinity also. So having f to be equal to infinity, we also have integral of f over E infinity to be infinity, so that integral of f is infinity and gamma of E infinity is infinity. Again we have f over integral of f over E infinity, so it will be same as gamma of E infinity in both the cases where mu of E infinity equal to 0 and mu infinity is greater than 0. So in both the cases we are having this, thus on ek and E infinity we have having two cases, comparing the case with ek and comparing the case with E infinity. Those two inequalities together implies gamma of E minus 1 by n times of mu E is less than or equal to integral of f over E with respect to mu, and this is less than or equal to gamma of E plus 1 by n times mu of E. So comparing both the cases, I have gamma of E minus 1 by n times mu of E to be less than or equal to integral of f over E with respect to mu, and that is less than or equal to gamma of E plus 1 by n times mu of E. And since mu of E is finite, we have mu of E to be finite at the start of the proof, and again n is an arbitrary number. Having mu of E to be finite and n to be arbitrary, we have gamma of E to be integral of f over E with respect to mu. This completes the proof of the Radon Nikodym theorem. Next, have a note that if gamma of E is the integral of f over E with respect to mu, then the function f is said to be the Radon Nikodym derivative of gamma with respect to mu, and also it is denoted by this denotion. So again, gamma of E is, if gamma of E is integral of f over E with respect to mu, then the function f is called the Radon Nikodym derivative of gamma with respect to mu, and it is denoted by as this. So, and we are at the one last theorem of this unit. It is Lebesgue decomposition theorem. Statement as follows: let X be mu be a measure space. It is a sigma finite measure space, and gamma be a sigma finite measure defined on the collection. Then we can find a measure gamma 1 which is singular with respect to mu, and a measure gamma 2 which is absolutely continuous with respect to mu, such that gamma is equal to gamma 1 plus gamma 2, and gamma 1 and gamma 2 are unique in the way of representation. So coming into the proof of the Lebesgue decomposition theorem, we have given that x b mu to be a sigma finite measure space. So x b mu is a sigma finite measure space. Also we have mu and gamma to be sigma finite measures on the measurable space. Sigma finite measures defined on the measurable space, say x b. So we have two things given. So x b mu is a sigma finite measure space, along with mu and gamma are sigma finite measures defined on the measurable space x b. We need to show that there exist two measures, say gamma 1 and gamma 2, in such a way that gamma 1 is mutually singular to mu and gamma 2 is absolutely continuous with respect to mu. So that also along with that, gamma is the same as gamma 1 plus gamma 2. So showing that there exist two measures such that the first measure is mutually singular with respect to mu and second measure is absolutely continuous with respect to mu, along with that gamma is same as gamma 1 plus gamma 2, will prove Lebesgue decomposition. To prove this, I will consider lambda to be summation of the two measures mu and gamma. So having lambda being sum of two sigma finite measures, given that mu and gamma are sigma finite, so lambda being sum of two sigma finite measures, again lambda is a sigma finite measure. Also, if I have lambda e to be 0, then that clearly implies mu of e plus gamma of e is 0. But we have mu and gamma to be measures. So as mu and gamma are measures, we have mu of e to be non-negative and gamma of e to be non-negative. So in order to this to be 0, we must have mu of e to be 0 and gamma of e to be 0. Since on choosing lambda e 0, we have mu of e to be 0 and gamma of e to be 0, we have both gamma and mu to be absolutely continuous with respect to lambda. So if lambda is 0, mu of t is 0. So mu is absolutely continuous with respect to lambda. Again, if lambda is 0, gamma is 0. So gamma is absolutely continuous with respect to lambda. So now I have two absolutely continuous functions with respect to lambda. In choosing that again lambda to be mu plus gamma, I came across gamma and mu to be absolutely continuous. Now having gamma to be absolutely continuous with respect to lambda and mu to be absolutely continuous with respect to lambda, by making use of Radon Nikodym theorem, I can find two non-negative measurable functions, say f and g, as follows. That is, if gamma of e to be equal to integral of g over e with respect to lambda, and say mu of e to be integral of f over e with respect to lambda. So this is what we have got by Radon Nikodym theorem. So if gamma is absolutely continuous with respect to lambda and mu is absolutely continuous with respect to lambda, I can find two non-negative measurable functions, say f and g, by gamma of e to be integral of g over e and mu of e to be integral of f over e, both with respect to lambda. So having this, I will construct two sets, say a and b, as follow. So a will be set of all x in x such that f of x is 0, and b will be set of all x in x such that f of x is greater than 0. So having a and b to be set like this, I clearly have x whole of the set to be a union b along with a intersection b to be empty. So I have a and b as follows, and x is a union b, a intersection b is empty. Also, if you find that if you see measure of b and mu of some set, it's defined as integral of f over that set. So mu of b will be integral of f over b with respect to lambda. And observe that B is the set of all x such that f of x is 0. Or you can interchange this. A is the set of f of x greater than 0 for my convenience, and B will be the set of all x such that f of x is 0. Then since B is the set of all x such that f of x is 0, we have integral of f over B is 0. So I have mu of B to be 0. So having constructed A and B to be like this, if I calculate mu of B, I am getting integral of f over B to be 0. Now I will say gamma of 1 of A. So if I need to say gamma 1 of A to be mutually singular with respect to mu, I need to define measures gamma 1 and gamma 2. So I will define measures say gamma 1 and gamma 2 from the collection B to 0 infinity union infinity by gamma 1 of E to be gamma of E intersection B, and again gamma 2 to be the measure from 0 infinity union infinity by gamma 2 of E to be gamma of E intersection A. So having to see gamma 1 of A, I need to have two measures gamma 1 and gamma 2, which is a mapping from the collection to 0 infinity. So gamma 1 is gamma of E intersection B, and gamma 2 is gamma of E intersection A. Clearly both gamma 1 and gamma 2 are measures. So now gamma 1 of A will be, with my definition, gamma 1 of A is defined as gamma of A intersection B. So gamma 1 of E is gamma of E intersection B. So if I take A in place of E, I have A intersection B. And I have A intersection B to be empty. So this is gamma of empty set. And since gamma of empty set is measure of empty set is 0, I have gamma 1 of A to be 0. So I had the first measure of B to be 0. Mu of B is 0. Mu of B is 0, and I arrived at gamma 1 of A is 0. So that we can conclude that gamma 1 is mutually singular to mu. So we have shown that having mu of B to be 0, gamma 1 of A is 0. So that gamma and mu are mutually singular measures. Again, from this clearly we have gamma to be gamma 1 plus gamma 2. So we have also proved gamma 1 is mutually singular to mu, along with gamma is equal to gamma 1 plus gamma 2. So we are now just remaining to prove that gamma 2 is absolutely continuous with respect to mu. So in order to finally see that gamma 2 is absolutely continuous with respect to mu, I will consider a measurable set, say E, such that mu of E is 0. So in order to see gamma 2 is absolutely continuous with respect to mu, I am considering a measurable set, say E, such that mu of E is 0. So considering mu of E to be 0 and mu of E, clearly we have defined it to be integral of f over E with respect to lambda. So since this is 0, we have this to be equal to 0, and integral of f is 0 imply f equal to 0 almost everywhere on the set E with respect to the measure lambda. So having mu of E to be 0, considering that E is a measurable set with mu of E 0, I have this defined to be integral of f over E, so that this implies f is equal to 0 almost everywhere on the set E with respect to the measure lambda. So having this f equal to 0 almost everywhere, by the sense of almost everywhereness, I have, if f equal to 0, then set of all x such that f of x is greater than 0 is of measure 0. Since lambda is the measure here I have with respect to f, here lambda measure of the set of all x such that f of x is greater than 0 is 0. So now having this, I will consider gamma 1 of f. So before we need to prove gamma 2 is absolutely continuous with respect to mu, I will consider f greater than 0 on E intersection A So we have lambda of E intersection A to be 0. Since f is greater than or z greater than 0 on the set E intersection A and lambda measure of such a set is 0, we have lambda of E intersection A is also 0. Now I will consider gamma 2 of E, and we have defined the measure gamma 2 to be gamma of E intersection A. So gamma 2 to be we have defined as gamma of E intersection A, and this must be 0 because lambda of E intersection A is 0 and we have gamma is absolutely continuous with respect to lambda at the start. So I took f greater than 0 on E intersection A because lambda measure is 0 for such f greater than on 0. So we have lambda measure of E intersection A is 0, and if I see gamma 2 of E, I have it to be E intersection A. This must be 0 as gamma and lambda are absolutely continuous. So I came at gamma 2 of E to be 0, having considered mu of E to be 0. So that assuming mu of E is 0, I came at gamma 2 of E is 0. So this implies gamma 2 is absolutely continuous with respect to mu. So this completes the proof of Lebesgue decomposition theorem, as well as this completes unit 4.